All right, today we're going to talk about building the brain of the game. We're moving way past AI that just, walks back and forth on a simple patrol path. We are diving deep into the world of agents that can actually remember, learn, explore, and even strategize. And the best part? We're going to see how this is all being built right now inside the V-engine using C++. But first, let's start with a question that I think every single gamer has asked at some point. Why do so many enemies in games feel, well, kinda dumb? You know the drill. You duck behind a wall and suddenly it's like you've completely vanished from their reality. You pull the same trick twice and they fall for it, every single time. That predictability, it's a huge immersion breaker, and it's the exact problem we're going to tear apart and solve today. So the first, and honestly the biggest hurdle here, is memory. Or, more accurately, the lack of it. Most game AI have the memory of a goldfish. If they can't see you in this exact moment, you might as well have never existed. And that leads to agents that just feel reactive, not truly intelligent. Now, there's a formal name for this problem, and it sounds a little intimidating. It's called a partially observable Markov decision process, or POMDP for short. It's a really technical term for a super simple idea. Your agent in the game doesn't see the whole map at once, right? It just gets an observation, basically what's in its line of sight right now. Without memory, that one little snapshot is all it has to work with. It's kind of like trying to solve a giant maze by only ever looking at the single floor tile you're standing on. It's almost impossible. So how do we fix this? Well, the solution is really a 1-2 punch. First, we need to give our agent a past, a memory. And second, we need to give it a reason to explore its future. And that comes from a little something called curiosity. Let's tackle memory first. So the memory part comes from something called recurrent neural networks. And inside the V-engine, this is handled by two specific C++ components you can see here, LSTM and GRU. Now, you can think of the LSTM, that's long short-term memory, as the deep thinking part of the memory. It has a cell state, which is perfect for keeping track of important long-term stuff like, hey, where did I last see that player? And then it has a hidden state for more immediate short-term context. The GRU is basically a more streamlined, faster version. It combines everything into a single hidden state, which makes it quicker and lighter on memory. The key thing to understand, though, is that both of these give our agent a persistent memory that carries over from one moment to the next. Okay, great. Our agent has a memory. Problem solved, right? Well, not quite. This can actually lead to a totally new problem. The agent can find a safe, kind of boring little loop and just stay there. Forever. It remembers its little comfort zone and has absolutely no reason to go see what's around that next corner. It's missing a spark. It lacks curiosity. And this is where the magic of the intrinsic curiosity module, or ICM, comes into play. Now, this is not about giving the agent more points for finding gold or loot. No. The ICM is a clever little system that rewards the agent for being surprised. It literally generates its own internal reward signal whenever it discovers something new or unpredictable. And the way it works is just this simple, beautiful loop. First, using that memory state from its LSTM or GRU, the agent predicts what it thinks is going to happen next. Then, it actually takes its action and observes what really happens in the world. And finally, it compares the two. The bigger the mistake in its prediction, the bigger the surprise, the more intrinsic reward it gives itself. This is what pushes the agent to actively seek out parts of the world it doesn't understand yet. It's brilliant. And the math behind it is just as elegant. Don't let the symbols scare you. The intrinsic reward is just proportional to the squared difference between what it predicted and what actually happened. In plain English, the more wrong the agent's guess was, the more curiosity points it gets. Simple as that. So now we have these awesome agents that can remember things and are driven to explore. But this creates a massive engineering problem. How in the world do you efficiently train a network that needs to remember a sequence of thousands upon thousands of events in a single game level? And yeah, here's the real problem. The normal way you train a network is with backpropagation. But that would mean calculating the error all the way backwards through every single step of an entire gameplay session. For a long level, that is just computationally insane. It would be unbelievably slow and eat up a ridiculous amount of memory. It's just not practical. The solution is this really clever technique called truncated ACK propagation through time, or TBPTT. And here's how it works. First, we chop up that super long gameplay sequence into smaller, bite-sized chunks. Next, we carry the agent's memory state forward from the end of one chunk to the start of the next one, so it never loses context.
Now here's the absolute genius part. We detach the gradient. This means when we're training on a chunk, the learning process stops right at the chunk's boundary. It doesn't try to flow all the way back to the beginning of time. And finally, we train the network using only the info from that one small chunk. It gives us the best of both worlds. We get to keep that crucial long-term memory without the crippling computational cost. And look, this isn't just some abstract theory. This is pulled directly from the V-engine's own specification for its LSTM component. It says right there, states detached for TBPTT at configured intervals. This detachment is a deliberate, essential optimization that makes training these advanced, stateful agents actually practical inside a real game engine. So, everything we've talked about up until now has been about making traditional reinforcement learning way, way better. But now, let's talk about a paradigm shift, a new way of thinking that changes the game entirely. What if we stop thinking about AI as just learning the best next action and start thinking about it as learning the entire language of gameplay itself? This slide really lays out the fundamental shift. On the left, you have classic RL. It's reactive. It learns a simple mapping, given the current state, what's my best action? But on the right, you have the decision transformer. It's predictive. It looks at a history of what's already happened and a desired goal for the future, and then it predicts the next action that fits that entire story. It's not just making a decision, it's continuing a narrative. To do this, it completely reframes gameplay into what are called trajectories. It literally treats gameplay like a language. You know how a large language model learns the grammar and flow of sentences by reading tons of text? The decision transformer does the same thing, but it learns the grammar of successful gameplay by analyzing these long sequences of three-part tokens. So what is this return to go thing? It's probably the most important new concept here. It's simply the total score the agent is expected to get from this exact point until the end of the level. It's the goal. So at the start of a game, you might tell the agent, your goal is to get 10,000 points. Then after it earns 100 points, its new return to go is 9,900. See? It's just a constantly updating target. And this leads to the absolute killer feature, goal conditioning. Because that target score is now an input to the model, a developer can directly control the AI's behavior and create totally different AI personalities on the fly. You want a super aggressive boss? Just prompt the model with a really high target score. You need a more cautious NPC that tries to survive? Prompt it with a lower, more conservative target. You're not just training a single AI anymore, you're directing a performance. Okay, let's put all of this together. What does this actually mean for the future of games? Well, we've gone from those simple reactive enemies to something that is just so much more powerful and flexible. We've essentially built a complete AI toolkit right inside the V-engine. We've got agents with recurrent memory so they can handle these partially observable worlds. We have intrinsic curiosity, which drives them to explore in really smart ways. We have efficient training through TBTT, which makes this whole thing practical. And finally, with the decision transformer, we have AI that can be directed with high-level goals, almost like a player following a playbook. And all this leaves us with a really fascinating final thought. When our AI is no longer just reacting, but is actively exploring, remembering, and executing on these high-level strategic goals given to it by a designer, are we even creating opponents anymore? Or are we creating something more, like co-authors of the player's own unique experience? It's a profound shift in what's possible, and it's all being built right now, fundamentally changing the relationship between us, the players, and the game itself.